Okay, so I promised you we would do a little bit of a review of trigonometry, and that's what's coming next. So it starts with circles, right? Trigonometry is all about circles. So let me start by reminding you about two formulas. So the area and the circumference, those are the two attributes of a circle that we're going to look closely at now, of a circle with a given radius, which we'll label the radius as r, it's what you typically do, are given by the following formulas. So A is the letter for area. So area of the circle is equal to pi times the square of the radius. So, you know, A is equal to pi r squared is how you might say it out loud to yourself. And the circumference, which you denote with the letter C, is given by 2 times pi times the radius, or 2 pi r is how you might say it out loud. So those are your two formulas for area and circumference. So for example, the unit circle, this is a particularly special circle, which is what? It's the circle with radius 1 centered at the origin. So its center is right where the x and y axis intersect. We're going to draw a picture of it down here in a moment. Its center is the origin and its radius is equal to 1, so that completely determines the circle, right? If you know the radius, that tells you how big the circle is, and if you know the center of the circle, then you know the location of the circle, so that entirely characterizes a circle. Well, in particular then, if its radius is 1, we can calculate the area and the circumference of the unit circle using these two formulas and plugging in 1 for the radius. I've got the wrong pen here. So the area of the unit circle is going to be given by pi times the radius squared, which is 1. So 1 squared, so you're going to have pi times 1 squared, which is just pi times 1. So the area of the unit circle is equal to pi. And the circumference of that circle is going to be 2 times pi times the radius again, which is 1, so it's just going to be 2 pi. So the circumference of the unit circle is equal to 2 pi. Now there's a consequence of that, and that is what this next remark is saying. So let's read this carefully and then we'll justify it, because this might seem like it's coming out of nowhere. It follows that every real number theta, which lies in the interval 0 to 2 pi, and this is referred to as a half open interval, by the way, and the reason for that is because 0 is included as an endpoint, but 2 pi is excluded as an endpoint. So this interval only contains one of its endpoints, so it's sometimes called half closed. That's just a half open interval. So what about this number theta? Any number theta in this interval determines a unique point on the unit circle, which, by the way, we're going to use this notation to represent the x-coordinate and the y-coordinate of this point. And then we're going to identify theta with the angle shown below. Well, there's no angle shown below yet because we still have to draw a picture. So this last part is not going to make sense until we draw the picture. So here's what we're going to do. We're first going to sketch this interval, 0 to 2 pi. Okay, we're going to draw the number line, but I'm going to draw it vertically, just mostly because of spacing issues, right? Think about the real line like that. You've got 0 and you've got 2 pi. So I'm really just sketching an interval. Right, and I'm going to include the endpoint 0, and I'm not going to include the endpoint 2 pi, but I'm going to shade everything in between. Right, I'm just sketching that interval 0 to 2 pi. Okay, so that is the real line, so I'm just going to write the r over there. Okay, so that is this interval. Let's draw also a picture of the unit circle. Okay, so it's going to look something like this. I'll just draw an x and y axis. The x-axis and the y-axis, and then our unit circle is going to look something like this. Here's the origin, its center, and it's got a radius of 1. It's not perfect, but I've done a lot worse, so I can promise you that, so that's not too bad. Now, this is going to be the point 1 on the x-axis, this is going to be the point 1 on the y-axis, this is going to be the point -1 on the x-axis, and this is going to be the point -1 on the y-axis. It follows from the fact that this circle has radius 1. But I'm not going to label those just because there's going to be a lot added to this picture as it is, and I just want to try to keep it as clear as possible. If I add too much, it's going to get really muddy. So I'm not going to label the point 1, but this is the point 1 on the x-axis. You know, I told you that. Okay, question. What is the distance from this point? If I were to measure all the way around this circle and get back to here, what would the distance be? And the answer is, we've already worked it out. The circumference, that's what the circumference of a circle is. It's the distance around the outside. It was given by 2 pi. Okay, so the distance around the circle is exactly 2 pi. What about the length of this interval? if you were to measure the distance along the real line from this point to this point, well, I'll turn it sideways so it's easier to see. You would just go 2 pi minus 0, which is exactly 2 pi. So this, if you think of this interval as a piece of string and you measured it with measuring tape, you'd get exactly 2 pi. That would be the length. Okay, so in other words, let me ask you, what would happen if I took this point and I pulled it over the top of the circle and I attached it to this point right on the x-axis, right where I highlighted, the point 1 on the x-axis, but I went on the top of the circle. And then I pull this end of the string this way and I attach it to the same place. So it gets put right on to the x-axis, right at the point x equals 1. What's going to happen? Well, if the circumference of the circle is exactly 2 pi, and the length of this string or interval is exactly 2 pi, it's going to get wrapped around perfectly and perfectly tightly, right? It's going to exactly wrap around this circle, no more and no less. And in fact, it's going to be perfect because this point and this end and this end both go to that same point. Well, there would be a collision if this point were solid. Then these 2 points would have to go to the same place. But because this is an empty dot, it's gonna wrap around that circle perfectly with no extra string. Right? That's why this works so nicely. Okay, now let's justify what we just said above. It follows that every real number theta between 0 to 2 pi. Okay, well let's draw some number theta down here. And I'll do it in green just to make it easier to match up with your eyes, or easier for your eyes to match up what's going on. Okay, so if I pick some number theta between 0 and 2 pi, well, that's going to be like part of the string, right? I'm going to shade it on this side just to highlight that fact. You're going to get a smaller piece of string. Okay, what would happen if you just took that piece of string and started wrapping it around the circle? Well, you might get something like this. Let's say it goes to about there, and then it stops. So, well, what can we say? Well, this is that point x naught, y naught that associates with theta. Whatever this point is, let me just make it a bit bigger so it stands out. So this is the point x naught, y naught. It's this point right there. Hope that's clear. Let me draw that, make that arrow a bit bigger. Okay, that's what the point x naught, y naught is. It's this point here. If I have a value theta between 0 and 2 pi, and I start from this point and go wrapping counterclockwise around the circle, at whatever point I run out of string, that's going to be this point here, which I'll write it down in a moment. It's going to be called the terminal point. Okay, so what's the significance of this? And it says we identify theta with the angle shown below. What is the angle? Well, go from the origin to that point and draw a ray that extends outward from the origin and goes through that point. Look what you've got. You've got an angle here, right? You've got an angle. And you might say, if someone asked you how big is that angle, you might, I don't know, if I had to guess in degrees, I'd try to say something like maybe 70, 75 degrees, right? I mean, because I know that if the y-axis and the x-axis form a 90-degree angle, this looks like it's certainly less than that, but it's more than half of that, so it's more than 45. I don't know, maybe 60, 70 degrees. If I had to guess, I would do that. But that's not how we're going to measure angles in this course. In mathematics, we like to measure angles in radians. And what does that mean exactly? It means instead of calling this an angle in degrees, you actually label this angle with exactly whatever this distance is, which was theta, right? And that's actually why I used the symbol theta here, because it's going to represent an angle. So that is what it means to measure an angle in radians. You identify this angle, the angle that this ray makes with the x-axis, you identify it with the arc length of this subsection of the unit circle that I've shaded with this, corresponding piece of quote-unquote string, if you will allow me to use that analogy. So that's what it means to measure an angle in radians. Okay, so and this is what it means to when we say that an angle theta in this half-open interval determines a unique point on the unit circle. It's this one here. Okay, so let me write a couple comments here. There's a couple notes I want to add. So 1, the point x naught, y naught is called the terminal point of this value theta, which lies in the half-open interval 0 to 2 pi. Okay, so that's the first thing I want to say. The terminal point in the sense that you ran out of string. At what point on the circle do you just run out of string? And the second note I want to say is that this notion, I'm going to word this a bit briefly, because if I try to word it precisely, it's just going to be too much, and I'll just spend half an hour writing it down. So I'll say this notion And what I mean by that is the idea of identifying a number theta between 0 to 2 pi with, first of all, a terminal point and then an angle. We can extend that to the entire real line. We don't need to stick between 0 and 2 pi, right? I could go, if I had a value of theta that was greater than 2 pi, well, then I would start here, I'd wrap around the circle, and then I would keep going. And eventually I would run out of string. If it was like 8 pi, for example, well, then I'd have exactly enough string to go around the circle 4 times. But I'd still have, at some point, I'd run out of string. What if I had a negative theta? What if theta was actually to the left of 0 on the number line? So if I took theta and I replaced it with a negative value way over here, well, then I would just go backwards around the circle, for the corresponding length around the outside. Okay, so you can do that for any real number theta. It doesn't have to be in the interval 0 to 2 pi. But I'm just going to write down a brief summary of that. I'll just say this notion may be extended to all real numbers theta. So to every theta in the set of real numbers. Okay, they're all going to have terminal points, and they're all going to be identified with corresponding angles. Okay, so that is how we can define the trigonometric functions. So that's what we're going to do now. Finally, we can write down the definitions. Once you understand this picture, the definitions of the trig functions are straightforward. It's just a matter of picking off the appropriate coordinates of the terminal point. So the trigonometric functions, sine, cosine, and tan, are defined as follows. Well, sine of this real number theta, just figure out the terminal point, and then once you have the terminal point, pick off the y coordinate. Sine of theta is equal to y naught. Cosine of theta is the x coordinate. So cosine of theta is defined to be x naught. And then tan of theta, that's the third trigonometric function, is defined to be the ratio, right? You take y naught and divide it by x naught. So it's equal to y naught divided by x naught, which, by the way, is also, you can also write this as sine of theta divided by cos of theta. So sine and cosine are defined in this way, and tan is defined as this ratio. So that's how you can get the trigonometric functions. And you see, it's not too hard to write those down. We did all the work by drawing this picture. This is really what the guts of it is. It's this picture. But once you have this picture lined up to write down the definitions of the trig functions, it's just a matter of picking off coordinates. Now there's also 3 other functions: cosecant, secant, and cotangent. Those are called the reciprocal trig functions. And they're defined as follows. If I want the cosecant of an angle theta, it's just 1 over sine of theta. If I want secant of theta, it's just 1 over cosine of theta. And then cotan, you might guess if you haven't already remembered, it's just 1 over tan of theta. Okay, so that is the definition of the 3 trigonometric functions, sine, cos, and tan, and the reciprocal trigonometric functions just follow by taking the reciprocal of each one, respectively.